So it's pleasure to provide and share the results of the research of the results of different directions that are includes the direction of intellectual services and providing of AI solutions like some service, and at the same time the ways of creation of prototyping of solutions based on the FPGA. So this is some crossing of directions of creation of AI as a services and creation of FPGA as a service. But the problem in this direction is how to provide such solutions for the end user to allow the integration with the systems. And to ensure this possibility, it's important to take into account the ways of organization of protection of such solutions during the distribution. And because of that, we consider the digital rights management issues, and we will try to cover the possibility of ensuring of such issues during the development process, and we will consider also the theoretical ways of how is it possible to perform the uh, ensuring of such solutions with use of theoretical ways of ensuring and identification of the exact chip. So we will try to cover the following things in our report. But before the accessing to the direct results, I propose to consider the current features of frameworks of the ways of work of such technology to allow the normal execution of the projects. And then we will be able to conclude how those technologies can be used together with solutions that provides the ensuring of light sensing processes or DRM processes. Well, so let's briefly consider the current status of the technologies. So one of the main possible feature of organization of FPGA projects that can be organized as a service is the organization of the runtime reprogramming of the chip. And in this case, for the end developer, the chip can be provided as some function that can be called like in C language call, like C call or OpenCL call. And in this case, for the end user, the entire computational process inside the FPGA chip is represented like some function that can be called each second, for example, or twice per second, or maybe one time per 10 seconds, but no longer, because the XRT or Xilinx runtime framework allows the duration of the computation no longer than 10 seconds or near this value. And this is the specific requirements of the operation system and the environment and drivers of the PCI Express card. So this is the revolution of the way of how the FPGA can be accessed, because traditionally or initially FPGA can be considered like some embedded systems that use some JTAG interface to allow the communication. But in this case, it's possible to perform the brief changes of the data between the components and between the host application, and it's possible to organize a fast communication between the elements, and it allows to perform really fast changes and calls of the chip. Okay, and everything is carried out by the XRT framework. In this case, it's necessary to follow the requirements of this communication, and it's happening like the encoding of the binary of the FPGA chip to the chip, initiating of the running of the chip, and returning back the data to the host. In this case, host application is connected over a driver and over this framework with with the operation system, and it allows the programmer to perform the communication with the chip, and it simplifies the process of creation of FPGA as a service. And technically, it allows to focus not on the communication, but just on the function that can be implemented. And in this case, a lot of pre-built and preliminary created binaries for some specific AI execution can be placed to the or collected at site of the host application, where it can be launched during few seconds, and then it's possible to directly perform the execution of required application, and it can be organized remotely. And to ensure this possibility, the following languages are supported. And for the AI development, it's typically some frameworks are used, like TensorFlow and Caffe. And also the Python is most frequently used for AI tasks at the moment. And because of that, the modern development environment like Vitis support the creation of such solution with such processes. And to work with that, it's necessary to follow the mentioned process of optimization of AI logic to ensure the possibility to transform the model of initial AI project and to place it after the optimization, pruning of the unnecessary connections, quantizing of levels to transform from float point representation to fixed point, and placing to the dark processing unit, deep learning or data processing unit, and this is a deep learning unit that allows to execute a lot of popular neural networks that can perform the implementation of the algorithms for popular image recognition and another kinds of popular AI solutions, AI-based solutions. Everything is executed on the digital platform created by this company. Actually, for the moment, it's AMD company, and all the software stack at both sides, host side for encoding and FPGA side for processing, allows to perform the acceleration. To do this acceleration, it's necessary to use powerful chips, sometimes with HBM memory, and there are a lot of chips, such like was mentioned during the previous report, the plenary report, and the chips that also allows to perform fast acceleration of AI solutions. And company propose the first purposes of the use of such fast FPGA accelerator cards are the acceleration of AI computation. At least for the moment, it's most interesting direction for such accelerations. And this card allows, for example, U55C as the next generation of U50 and U280 cards the possibility to work with up to 16 gigabytes of on-chip memory with the ability to transfer up to 460 gigabytes per second, but the next chip and next card that already announced but not available yet allows the work with 16 gigabytes, sorry, 32 gigabytes and doublet performance of this on-chip memory that allows to perform a lot of computations inside the chip, because this memory is directly placed in the same package as the chip, and use interconnects to perform the communication. And the installed in the data centers of such hundreds and thousands of such cards allows to perform the centralized implementation of the services, FPGA as a service, and AI with FPGA-based implementation as a service. But while it's possible to deploy everything, the most important question, how to ensure the light sensing processes for such projects, while the end user can use some third-party libraries and solutions and components of AI. It's necessary to ensure the ways to perform the control of execution to prevent some unwanted and unmanaged process of execution of solutions. And to ensure this process, it's necessary to solve the most important problem of ensuring the control of licensing process of such solution. And in this case, the aim is to find the possible ways of licensing and applying of such process to improve the ways of the digital right management processes for AI and machine learning systems based on FPGA. And to solve this issue, it's necessary to perform the following tasks: to analyze the possible ways of ensuring of DRM, find possible options to identification of FPGA solutions, to propose the most promising directions of possible DRM implementation for FPGA services that allows to identify the exact instance, exact chip of FPGA, and allows the execution or prevent the unmanaged execution. And of course, to provide the solutions with such implementations. So, based on that and based on the considered ideas, it's possible to analyze the structure of current status of AI as a service with FPGA implementation, where it's possible to place the FPGA chip as a basic level or layer of such computations that can be connected together at the FPGA card. And with this card, there is a built-in software, some software that allows the communication over the PCI Express. It called shell, some shell inside the protected part or static region of FPGA. And with this, exactly this part, the host application can communicate. The next level is actually the host PC or station where such cards are connected together, maybe up to 8 per one controller or even more. And at this level, we can obtain the FPGA as a service layer, where it's possible to organize the communication with such elements, with such host solutions, But above all that, there is a FPGA-based artificial intelligence layer where it's possible to perform the computations with the implementation of some elements of AI that is based on neural networks. So actually, this is the general classification of place of FPGA in such services, and to perform the protection of such solutions, it's necessary to find the ways how it's possible to identify exact chip inside this structure of the service. And to identify the exact chip, it's necessary to find the possible way how to do it, how it can be done using the traditional ways and ideas. And based on the performance analysis, the following ways of theoretically possible ways of identification of the exact chip were proposed, and they are starts from the commonly and widely used information like email address, user-based data, and phone number, some USB key like external component, then the set of information based on the system board like MAC address of the network, volume ID of the connected device, storage device, some information about the basic input output system of this system board, and trusted platform model that allows the execution of some trusted processes. And this theoretical level is based on the exact PCB and system board with the chip. And next level is based on the board itself, the card number and part number of the board. And this information sometimes is available for the chip, but sometimes no. And it's not technically useful sometimes to use it, but it's necessary to take into account that this possibility exists. And the most interesting and most promising way of identification that really provides an ability to perform the identification of the exact chip is usage of physical unclonable functions implemented inside the FPGA, because the implementation of physical unclonable function allows to find and maximize the difference between few chips, two different chips provided and created in the same technological process. So it means that functionally there is no difference between those two chips. And functionally it's impossible to differ what the number of the chip, because all the tests will be passed at the same way with those two chips. But with use the technique of physical unclonable functions, it's possible to organize the identification of the exact instance of chips that functionally completely identical. And it's possible to implement with maximizing of difference of the delays between different parts of the chip inside the chip, between different passes inside the chip, with use the oscillating and comparison of some ring oscillators inside the chip, with use of multiplexers emulating of the memory, static memory, and with thus unstable and uh, maybe generating of a random number or true random number generating, it's possible to perform the identification or some probabilistic identification of such elements. And with increasing of number of such parallel registers and bits number, it's possible to maximize the probability of identification of such chips. But it requires the development, and it requires the running of the process inside the chip, of course. But some identification ways allows the identification without the running of FPGA implementation. So, based on this analysis, it's possible to find the possible ways of such identification of the exact instance. But the some chips, some modern chips, allows to use some built-in solutions to perform the identification of the chip that simplifies this process. It's not available for all chips, but some chips allows it. And it can be done using the DNA port. It's not the unique way of identification, but it's one of possible identifications. And it's also possible with use another ways like USR access. DNA port allows the 64-bit and 128-bit dependence on the exact implementation, communication with the chip, and it's possible to perform the reading bit by bit using the shifting of the information inside. But the limitation of the use of such DNA port inside the chip is the limited frequency to the process of activation of this component. It can't be faster than 100 megahertz. This is the limitation. And while the chip can run up to 500 megahertz, it's some significant limitation of the speed in five times of the final performance. But from the point of view use of overclocked modes of running of FPGA accelerators, while it's possible to achieve 700 of megahertz and even higher, it's significant limitation, and it's necessary to use PLL to clock this component if it's required. Another way of identification of the exact component is use the user access component, but instead of the DNA that allows to identify the chip die inside some part of the chip, and in some components there are three parts in same package. The user access is a part of the binary stream generated during the compilation, and the developer can assign the exact user access over the parameter to the compiler to provide the exact code of this build. So it's technically can't be used directly for identification of the exact chip, but for identification of the exact build version or the exact build instance, even for the same version. So technically it's possible to use this user access component to identify the exact binary even of the same version. But there are the same limitations of such component of use with a frequency. And let's consider the example of the use of the DRAM projects from the one of associated with AMD company that provides the digital right management ways for such solutions. And this company allows to perform the work with built-in kernels, and we will consider how is it working. But in this practical case, let's consider that this activation logic and the DRM IP or DRM kernel or kernel DRM controller, to be clear, uh, also connected to the 86 bits port of chip DNA. And you can see that there is such connection inside the logic of this DRM controller. So this controller is connected to the chip DNA to allow the identification of this chip. The investigation of internal implementation of this controller, obfuscated controller, that use the standard of obfuscation, and this standard allows to perform such centralized obfuscation of the code, and this code then can build. This standard is IEEE 7035. This is the standard of encryption, while the developer can use this standard and then is capable to perform the acceleration of such solutions. Well, let's consider how is it implemented inside the chip. While you can see the three independent super logic regions connected together inside single FPGA chip, and each such block contains own DNA port, and there are few possible ways of implementing it. 1 second. Well, so let's consider the implementation of such approach of DRM. Use some centralized server that performs the communication with the host application, and with the libraries associated with the DRM logic that use the hidden way of communication with the kernel, not the same as the user use. And to implement this possibility of communication, it's necessary to specify the exact basic address of the kernel to the host application and to the libraries, obfuscated libraries at the host side. Inside the FPGA kernel, the DRM component can be placed, and this component is also obfuscated using this standard, IEEE 1735. And the communication with the kernels can be happening over AXI4 interface, and it's possible to connect any number of user kernels inside this logic. This way of communication is not documented, but it's possible to use such ways of communication because this company working intensively with a vendor of FPGA logic and FPGA environment, and they use undocumented or not published yet features that allows the communication of the DRM logic in the way that not available directly for the end user, but technically it can be implemented in this way. And in this case, the protected DRM logic can be connected to end user component using the independent AXI for communication buses. It's possible to perform the communication with this kernel to provide the activation logic and to provide the usage event, and all this information will be passed directly to the centralized server. The deployment process of such solutions can be done with use of integration of the DRM component to the project. Then it's possible to build the environment with the host application, then place everything to the Docker instance, and then it's possible to publish this Docker image at the website of Xilinx or AMD with the application store. So that's why we considered the ways of DRM protection, and I will answer for all the questions that can be based on our current report. Questions, please.
So yeah, let's have this question session part. Do you have like any questions you want to address?
It will be interesting to share the experience of work with such DRM solutions, with AI solutions, with FPGA-as-a-Service solutions. So we will be happy to answer for all questions.
Okay, so if no questions, let's maybe then continue. Thank you, Artem, very much.
May I ask a question?
Yeah, sure.
You were talking about using FPGA for different purposes, like card number or email or USB. So I don't completely understand how that works. I mean, it's one FPGA, but with different unique possibilities for each of types. Yes, about that.
Okay. We tried to consider the possible ways of identification of the exact accelerator card installed in the data center. And each card, modern card, contains some interfaces connected to the FPGA chip over some integrated circuits that allows this communication, like interface. And on those cards, there are a lot of network cards installed, and of course the possible USB connectors. And in this case, we're talking about the possibility of use thus on board, on system logic, to perform the identification of the instance of the project inside the chip. So we're trying to associate the exact instance, the exact FPGA accelerator card with some unique ID or some unique feature that allows to identify this instance to ensure that only one or few allowed parallel running instances of our application, to protect the application, to prevent the unwanted use or unmanaged use of this application, to ensure the rights management. So in this case, we are trying to use the onboard features. And while the network adapters are available for FPGA, we technically can try to use some features. At least we can consider this possibility while it's theoretical analysis.
Yes, I now understand. Thank you.
Okay, you're welcome.
Okay, any other questions? Okay, so if no any questions, thank you, Artyom, for this topic, for this presentation. Now let's